Video, we're going to learn about decoding the CNN architecture, a comprehensive block diagram analysis. Introduction. A convolutional neural network is a type of deep learning neural network architecture commonly used in computer vision. Computer vision is a field of artificial intelligence that enables a computer to understand and interpret the image or visual data. When it comes to machine learning, artificial neural networks perform really well. Neural networks are used in various datasets like images, audio, and text. Different types of neural networks are used for different purposes. For example, for predicting the sequence of words, we use recurrent neural networks, more precisely an LSTM. Similarly, for image classification, we use convolution neural networks. In this block, we are going to build a basic building block for CNN. Types of layers. Input layers. It's the layer in which we give input to our model. The number of neurons in this layer is equal to the total number of features in our data. Hidden layer. The input from the input layer is then fed into the hidden layer. There can be many hidden layers depending on our model and data size. Each hidden layer can have different numbers of neurons, which are generally greater than the number of features. The output from each layer is computed by matrix multiplication of the output of the previous layer with learnable weights of that layer, and then by the addition of learnable biases followed by activation function, which makes the network nonlinear. Output layer. The output from the hidden layer is then fed into a logistic function like sigmoid or softmax, which converts the output of each class into the probability score of each class. CNN architecture. The convolutional layer applies filters to the input image to extract features. The pooling layer downsamples the image to reduce computation, and the fully connected layer makes the final prediction. The network learns the optimal filters through backpropagation and gradient descent. How convolutional layers work. Convolutional neural networks or COVNETs are neural networks that share their parameters. Imagine you have an image. It can be represented as a cuboid having its length, width, and height. Now imagine taking a small patch of this image and running a small neural network called a filter or kernel on it, with say k outputs and representing them vertically. Now slide that neural network across the whole image. As a result, we will get another image with different widths, heights, and depths. Instead of just R, G, and B channels, now we have more channels but lesser width and height. This operation is called convolution. If the patch size is the same as that of the image, it will be a regular neural network. Because of this small patch, we have fewer weights. Mathematics involved. Convolution layers consist of a set of learnable filters having small widths and heights and the same depth as that of input volume. For example, if we have to run convolution on an image with dimensions 34 cross 34 cross 3, the possible size of filters can be A cross 3, where A can be anything like 3, 5, or 7, but smaller as compared to the image dimension. During the forward pass, we slide each filter across the whole input volume step by step, where each step is called stride, and compute the dot product between the kernel weights and patch from input volume. As we slide our filters, we'll get a 2D output for each filter and we'll stack them together. As a result, we'll get output. Volume having a depth equal to the number of filters. The network will learn all the filters. Layers to build ConvNets. A complete convolution neural networks architecture is also known as ConvNets. ConvNet is a sequence of layers, and every layer transforms one volume to another through a differentiable function. Types of layers is classified based on the dataset. Let's take an example by running a ConvNet on of image of dimension 32 cross 32 cross 3. Input layers. It's the layer in which we give input to our model. In CNN, generally, the input will be an image or a sequence of images. This layer holds the raw input of the image with width 32, height 32, and depth 3. Convolutional layers. This is a layer in which it is used to extract the feature from the input dataset. It applies a set of learnable filters known as the kernels to the input images. The filters or kernels are smaller matrices, usually 2 cross 2, 3 cross 3, or 5 cross 5 shape. It slides over the input image data and computes the dot product between kernel weight and the corresponding input image patch. The output of this layer is referred as feature maps. Suppose we use a total of 12 filters for this layer, we'll get an output volume of dimension 32 cross 32 cross 12. Activation layer. By adding an activation function to the output of the preceding layer, activation layer add nonlinearity to the network. It will apply an element-wise activation function to the output of the convolution layer. Some common activation functions are ReLU, max, 0, x, tan h, leaky ReLU, etc. The volume remains unchanged, hence output volume will have dimensions 32 cross 32 cross 12. Pooling layer. This layer is periodically inserted in the coordinates and its main function is to reduce the size of volume, which makes the computation fast, reduces memory, and also prevents overfitting. Two common types of pooling layers are max pooling and average pooling. If we use a max pooling with 2 cross 2 filters and stride 2, the resultant volume will be of dimension 16 cross 16 cross 12. Flattening. The resulting feature maps are flattened into a one dimension vector after the convolution and pooling layers, so they can be passed into a completely linked layer for categorization or regression. Fully connected layers. It takes the input from the previous layer and computes the final classification or regression task. Output layers. The output from the fully connected layers is then fed into a logistic function for classification tasks like sigmoid or softmax, which converts the output of each class into the probability score of each class. Advantages. Good at detecting patterns and features in images, videos, and audio signals. Robust to translation, rotation, and scaling invariance. End to end training, no need for manual feature extraction. Can handle large amounts of data and achieve high accuracy. Disadvantages. Computationally expensive to train and require a lot of memory, can be prone to overfitting if not enough data or proper regularization is used, requires large amounts of labeled data, interpretability is limited, it's hard to understand what the network has learned. Conclusion. In conclusion, this presentation has provided a comprehensive block diagram analysis of the CNN architecture, shedding light on its key components and functionalities. Understanding CNNs is crucial for leveraging their potential in various domains. Thank you.